Okay, so what we're going to cover in this video is KSP. KSP is the solubility product constant. So if you kind of think about your equilibrium constant, KEQ. KEQ was the concentration of products over the concentration of reactants for a system that's at equilibrium. KSP is very, very similar, except for with KSP, we're looking for the dissolving of a specific solid at equilibrium. Okay, so if you remember your KEQ rules, we don't include solids in KEQ. Well, we likewise don't include solids in KSP. So if I were to look at just a general equation where I had something solid that dissociates into two things that are aqueous, my KSP expression would be KSP equals the concentration of the positive aqueous thing times the concentration of the negative aqueous thing over 1, because we are leaving out the solid. We don't include the solid just like we didn't include it in KEQ. So, and here's where we have to kind of reconcile a little white lie that I have told you. If you are not going on to take AP Chem, you can perfectly live in the world where things that are insoluble do not dissolve. But that's really not true. Okay, so most insoluble salts, things that are, we say, insoluble on our yield reference packet, are actually a little bit soluble, slightly soluble. All substances are soluble to a point. Some of them are just quite simply far less soluble, to the point of, we would say, for most uses, they are insoluble. But again, that is a tiny little white lie that we have told you. They are actually soluble, just very, very slightly so. So when we are looking at KSP, we are looking at these solids as they dissociate. So the first thing that we need to cover is, how do I write a KSP expression? So before you can write a KSP expression, you need to write a dissolution equation. Okay. So let's get a little review practice with that. So I have aluminum hydroxide. So I'm going to write the dissolution equation for aluminum hydroxide. So I'm going to start with aluminum hydroxide, which we know is a solid, and it's going to dissociate into its ions. We're going to have aluminum plus 3 as one of the ions, plus 3 OH minus 1 as the other ion. So there's our dissolution equation. Now we need to take that and we need to write a KSP equation, a KSP expression. So we know we're going to leave this out because it's a solid. So I'm only going to be dealing with my 2 ions here. And it's just like I did in KEQ, except for I'm going to write KSP instead of KEQ. So KSP is equal to the concentration of the aluminum times the concentration of the hydroxide raised to the 3rd power, because there's 3 of them. Okay. All right, let's do another one. So silver sulfide, so Ag2S solid. It's going to break down into 2 Ag plus 1 plus S minus 2. And again, leaving out our solid is going to give me a KSP of Ag plus 1 squared times S minus 2. Okay. All right, and then the last one we're going to do PbCl2 solid is going to dissociate into Pb plus 2 plus 2Cl minus 1. That's going to give me a KSP expression of Pb plus 2 and Cl minus 1 squared. Okay, so very similar to what we saw in our KEQ work. This time we're just going to be looking at a bunch of solids that are dissociating, as opposed to any sort of substance with gases or aqueous ions. So this is always going to be your solid with your aqueous ions. Okay? So there's 2 different types of equations that you will be asked asked to do, at least in this class, with KSP. So we're going to be asking you to find KSP, to solve for KSP. So obviously this would be the first step of that. And then the second thing we'd ask you to do is to solve for the concentration of these guys here, which is called molar solubility. So let's run through a couple examples with that. All right, so again, two types of KSP, calculating KSP, and then solving for molar solubility. So let's do KSP first. So let's look at our first problem here. Calculate the KSP of calcium sulfate if the solubility of I should not say the solubility of KSP. I should say the solubility of calcium sulfate. Sorry, guys. If the solubility of calcium sulfate is 0.67 grams per liter at 25 degrees Celsius. Okay. Well, if you think about what we saw on the last page, those are concentrations. So we're going to need to do some conversion for this. If you're given the concentrations or the molarities initially, then you wouldn't have to do this step. But because I gave it to you in grams, I'm asking you to just do a little bit more work. So we know that we have 0.67 grams of calcium sulfate, so I need to get the molar mass of my calcium sulfate first. So my molar mass of calcium sulfate is 136.15 grams per mole. And I know I can use that to do my conversion to moles. So 0.67 grams times 1 mole over 136.15 grams gives me 0.00492 moles per liter. It told me it was grams per liter, so making the jump to moles per liter is pretty easy. All right, so now, what else do I need? Well, I'm going to find the KSP of this solid, so I need to write a dissolution equation and then a KSP expression. So CaSO4 solid is going to give me Ca plus 2, the ion, plus SO4 minus 2, the ion. And this is nice because I only have one of each, so it's going to make my KSP really easy. KSP equals the concentration of Ca plus 2 and SO4 minus 2. Oops, let's get that over so you can see it. All right, so now what do we need to do? Well, I know that per liter, 0.00492 moles are going to dissolve. Well, what does that mean? Each of these represents those moles that are dissolving, right? So when this dissolves, I'm going to make 1 mole of this and 1 mole of this. So I can take my KSP and actually change it to make it a little easier. You don't have to do this because I could just plug this number in for both of these and call it a day. But you know what I like to tell you, the less you have to type in the calculator, the less likely you are going to make a calculator type of mistake. So if both of these are going to be the same value, can we call them x? I think we can. So KSP equals x times x, which means that KSP equals x squared. So that just made my typing into the calculator math a lot easier. So, I'll just bring it over here so a little bit more room. KSP equals 0.00492 squared, and that gives me a KSP value of 2.4. I only have 2 suffix times 10 to the minus 5th. Easy peasy. Okay. And just like KEQ, KSP is unitless. Yay, unitless. Unitless makes things nice. Okay, so let's do another example of this. The solubility of bismuth sulfide, that's kind of an odd one, is 1.0 times 10 to the minus 15 moles per liter. So what did they give me? They gave me molarity, which is nice. I don't have to do any pre-calculations. It's already there for me. Calculate the KSP value. All right, so this one we're going to add a new tool to our toolbox that we have not seen necessarily before with this KSP. So go with me here as we write our equation. Bi2S3, I know that's my solid, is going to dissociate into 2 Bi plus 2 plus 3s minus 2. That means that my KSP is going to be BI plus 3 squared. Oops, my bad, guys. That should be a 3. BI plus 3 squared times S minus 2 cubed. Okay, well, that part we've seen before, so what's the new thing? So when I'm finding KSP, I have to recognize that every time one of these breaks down, I'm going to get 2 of these and 3 of these. And you're like, well, but you already have that there with the exponents. I do and I don't. There is a stoichiometric ratio that we have to make sure that we are maintaining. So we do something that's a little weird here. And it kind of caught me by surprise the first time I did it. Like, why would we be doing that? And it's just kind of one of those things that it's because there's a stoichiometric ratio. So when I take this, and I remember how up here we turned these into x, watch what happens. So KSP is going to equal 2x squared times 3x cubed. Okay, the 2 here and the 3 here. And again, that's because we're trying to maintain that stoichiometric ratio. That think about this is for each mole. Well, I'm making 2 moles of that, and I'm making 3 moles of that. So we got to maintain that ratio. So let's try to clean up this hot mess of coefficients and exponents. So 2 squared is going to give me what? 4. So this is going to be 4x squared times 3 cubed. So 3 times 3 is 9 times 3 is 27. So 27x cubed. That's going to clean up to 108 x to the 5th. If you don't want to do that and you want to just plug into this, you're going to get the same answer. Again, I find it a little bit easier to not have to do all that. The less I have to type in my calculator, the better for me. Okay, so now all I got to do is plug in. So KSP equals 108 times x, 1.0 times 10 to the minus 15 molar to the 5th, and that gets me a KSP value of 1.1 times 10 to the minus 73. And that is a tiny, 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 tiny number. Okay, so what does that mean? Well, think about what KSP is. So KSP is products over reactants. And it just happens to be that we ignore our reactant because it's a solid. So if this value, this KSP, is so much less than 1, we know that the product side is definitely not favored. We are for sure favoring the reactant side. So what does that mean in this case? Well, what was on my reactant side? It's my solid. So this is extremely not very soluble. Okay? So this has a very, very small KSP value. So only a tiny, tiny, tiny amount is going to dissolve. Okay? So let's compare that to up here. So 10 to the minus 5th, which we would normally think of as a pretty small number until you see 10 to the minus 73. So in this one, the products are still not favored, but it's a little closer than it is down here. So this, I would say, is a little bit more soluble than this, but both of them are still not very soluble. But you've got to look in terms of degrees. This is real, super, super not soluble. This is only like real not soluble. Okay, got to get those degrees in there that we think about. All right, so pretty much all these problems are going to be the exact same way. You're going to be given your molar solubility or given information to get molar solubility. Write out your KSP words. Write out your KSP expression and plug and chug. Okay, easy enough. All right, now let's go to the other type, solving for molar solubility. All right, so in the first one, calculate the solubility of copper 2 hydroxide if the KSP value is 2.2 times 10 to the minus 20. So with this one, what we're looking at is we are now solving for x. You have KSP. So we're going to have to go back and we're going to have to solve for the x to figure out what's the solubility moles per liter. It would help if I could show you the question. Sorry, guys. So first thing we need to do is what? Yes, we need to write our dissolution. So let's start with that. CuOH2 solid, Cu plus 2 aqueous plus 2 OH minus 1 aqueous. All right. And then what? Oh, that's right, KSP. So KSP equals Cu plus 2 OH minus 1 squared. Okay. So we need to get our x term because we want to solve for x. So let's get an x term. So that means that KSP is going to equal, well, this guy's just going to be x. And we've got 2 OH, so this one's going to be 2x squared. So we know 2 times 2 is 4. So we're going to have 4x squared and x, so that's going to give us 4x cubed. All right, so now KSP is equal to 4x cubed. All right, now what? Well, I know what KSP is. I need to solve for this x. So I need to rearrange my equation so that I can solve for x. So how do we do that? Arithmetic, which you should know. Okay. I need to get x by itself. So I'm going to divide both sides by 4. So KSP over 4. And then how do I get the cubed off? Take the cubed root. So let's rearrange this bad boy up here. That means now x equals the cubed root of KSP over 4. So then what? Plug in your KSP. Easy math, guys. Easy math. X equals the cubed root of, what was my KSP? 2.2 times 10 to the minus 20 over 4. Algebra math, yay, calculator. Aren't you glad you know how to use your calculator? X equals 1.8 times 10 to the minus 7 moles per liter. Or, what did I say instead of moles per liter? Molarity. Okay, pretty easy. I mean, little arithmetic you got to remember, but we just did all of this when we did KEQ. So those arithmetic skills shouldn't be too terribly rusty. All right, let's look at one more. Calculate the molar solubility of copper 2 iodate, given that you have a KSP value of 1.4 times 10 to the minus 7th. All right, so what do we need to do here first? Oh, what did I do on the last one first? Write your dissolution equation. So CuIO3 2 solid produces Cu plus 2 aqueous plus 2 IO3 minus 1 aqueous. All right, so what does that mean? Oh, KSP equals Cu plus 2 IO3 minus 1 squared. This seems like awful similar to what I just did up here. Okay, you are going to start to notice some patterns. So if I have one thing that I only have one of, and I have the other thing that I have 2 of squared, what does my KSP end up as? KSP is going to be 4x cubed, right? X, 2x squared, 4x cubed. All right. So how do I solve for x? Same way I did up here. Rearrange, magical arithmetic. That's going to give me x equal to cubed root of the KSP over 4. Plug and chug. X equals the cubed root of 1.4 times 10 to the minus 7 over 4. And that gives me an x value of 3.3 times 10 to the minus 3rd molar, or moles per liter. Okay. All right. So the last thing I want to show you is just kind of a good mental checkpoint. How to compare your KSP value. So let me just give us a little bit of space down here. So what if I gave you a question that sounds like this? in which beaker are more Cl- ions present, given AgCl solid is going to produce, you guessed it, Ag plus 1 aqueous plus Cl minus 1 aqueous. And, oh, what beakers? These ones I'm about to draw for you. So 2 beakers. We will call them beaker 1 and beaker 2. And this one has a KSP equal to 1.0 times 10 to the minus 9. This has a KSP equal to 1.0 times 10 to the minus 17. All right, so think this out. I gave you KSP. KSP represents what? KSP is products over reactant, right? Chlorine ion is a product. So I'm looking for the one that's what? Closest or farthest from 1. I need the one that's closest to 1. So 10 to the minus 17th, 10 to the minus 9. This is a heck of a lot closer to 1. That means that this is going to have more products at equilibrium. So this one, beaker 1, would have the most ions. Okay, hope that was helpful.